Evening, everybody. It is 5 o'clock Thursday evening. Time for a little Calc 2. All right, so let's talk a little bit about what we're going to do today, where we're at, and where we're going. So today we're going to look at parametric equations. You guys have gone through the online lesson. There's a few things I'm going to highlight about parametric equations. We'll look at an example of finding the derivatives with parametric equations, how we can graph them. Then I'm going to let you guys work on some a worksheet where you're going to work on some calculus with parametric equations. And tonight you'll have the second of 3 take-home problems available. The one for module 2. Because it's going to encompass what we're doing tonight. So that should show up in that take-home problems folder after class tonight. So you can get started on that. Like I said, when it comes to the take-home problems, the reason I give them to you early is to give you time to work on them. That way, when it comes time to study for the exam, you have the take-home problems done and you can focus on the exam. Okay, well, let's jump on into parametric equations. So I've got Desmos up here. I've got some examples in here that we're going to look at in a little bit. Basically, the idea behind parametric equations is, what happens is in 2D or in 2 dimensions in the XY plane, we end up with any separate equations for X and Y in terms of some third parameter, in this case T, hence the name parametric equations. For those of you guys who are going on to Calc 3, there'll be parametric equations in terms of 3 variables. There'd be a Z of T, and it makes a lot of cool things that we're able to do. So let's take a look at a graph here. So let's say our X of T is 2 square root of T, and Y of T is 5T plus 4. And to put these in Desmos, all you got to do, let's move that towards the top. See how these are in parentheses? The first one in your parentheses is your X. And actually, let's use T. You can actually use any letter you want, but I just want to be consistent. And 5T plus 4. Now notice I only get a segment of the graph. This is something that I can't emphasize enough with parametric equations. You got to give a range on the parameter to create the graph. So for instance, if I say I'm going to let T go from -1 to 1, I get a little bit more of the graph. If we go up to 4, actually negatives won't give much of this because of the square root of T. So let's put that back at 0. But we can see that we're getting the right-hand side of this graph. We're not getting anything over here because X cannot be negative. Now, one of the things we can do with parametric equations is we can convert them, when possible, to rectangular functions. It's not always possible, and I'll show you why here. We'll look at some graphs. But if we wanted to see what this looked like in rectangular, we do a process that's called eliminating the variable. And there's nothing really crazy going on here. We solve for a variable in 1. So maybe on this one, we solve for T. So we might divide both sides by 2. So we get X over 2 equals rad T. Square both sides. And we get T equals X squared over 4. And what we do is we plug that into this one, which would give us Y equals 5 times X squared over 4. This is called eliminating the parameter, or 5/4 X squared plus 4. The plus 4 makes sense. Look at the bottom of this guy right here. And if we want to, check it. So Y equals 5 divided by 4, X squared We can see that parabolic shape plus shift it up 4. Notice we get the exact same graph. Now, a couple interesting things that I want to point out here. Number one, when we graph something in rectangular coordinates, which is our y equals 5 course x squared plus 4, we get the entire graph plotted over the entire domain of x. All right. That's a little different than what we got with the parametric, where we have to basically tell it what range we want the parameter to be seen over. The other thing that's happening that I'm sure you noticed is, hey, now we get the left-hand side. We weren't getting that before. That's because of what our step was in eliminating the parameter right here. Because to do that, we squared both sides. What that did is that allowed for both positive and negative x values. But based off of our parametric equations, based off of this piece right here, we know that x does have to be greater than or equal to 0. So we're really only looking at the right-hand side, and that's how they match up. Again, it was in our solving that basically allowed for negative x values, which our original parametric equations do not. So that's the basic idea behind parametric equations, is that instead of y as a function of x, x and y are functions of some third parameter. And a lot of times we use t, but we don't have to. Basically, it can be anything except for x and y. But it's going to allow a lot more flexibility. So let's get these out of here. Because what it does is it allows us to plot things that aren't functions. So what I'll tell you is you guys have actually seen parametric equations before to be here. They may not have been called parametric equations, but you've seen the parametric equations x equals cosine of t, y equals sine of t in trigonometry, which creates our unit circle. Okay, a circle with radius 1. These are parametric equations because x and y are being defined in terms of some third parameter. And what's really cool about this is now we have a way of plotting something that's not a function, right? This does not pass the vertical line test. If we drop vertical lines in there, they're going to hit in more than 2 places. So the way I always like to explain it is when, functions are great. The nice thing about functions is every input has a unique output, and we're guaranteed that. The downside is because of that requirement, we're restricted to graphs that must pass the vertical line test. Well, what if we want to graph a circle? There's going to be a lot of things that we want to plot that are not going to pass the vertical line test. So how do we do that? Well, parametric equations is one of those ways. It's, I always like to use the matrix analogy. It's kind of like when we're plotting functions, we're in the matrix because we're under a set of rules. Well, once we go to parametric equations, that set of rules is off. As I'm talking about this, I'm just kind of introducing them very generally. If you guys have any questions, let me know. We'll start to dive into some stuff here a little bit more mathematically in a second, but I just want to show you some interesting things on the graphs. Let's move these out of the way.
So are the main things you need to plot a parametric equation just the x and y value, and then the limit, and then the limits of what you're plotting?
Yes. So you would need basically an equation for x, one for y, and then some sort of range for t. Yeah. Did that answer your question, John? Sorry.
Yes, that answered my question. Thank you.
Okay. And guys, you can plot these in your graphing calculator. If you go into mode and change function to parametric, if I can get it to change. All right, how about this? Enter. So now it's on parametric. So now when I go to my y equals, it'll take in a y1 and a y2. And if I go to the window, this t step or sorry, the T min and T max, that's the T range. So right now it's set to go 0 to 2 pi. So, if you wanted, if you wanted to do sine, if we want to do the unit circle in here, okay, sine. So you do have the ability, now it's not circular because the way it's zoomed, if we do a zoom square, we should get a bit more circular shape. Zoom in on that. Just one other thing that you can do. If you wanted to try and figure out what limits make sense, this is another way of playing with it. Like I said, right now it's 0 to 2 pi, but if you wanted to see, okay, well, what happens if I do 0 to pi? Putting in pi's probably would have been quicker. That gives me the left-hand side of the circle. So the graphing calculator can plot all the stuff that we're talking about today. We're going to use Desmos. It's a little bit more nicer picture for on the computer, but graphing calculator can absolutely do all our parametric equations. Okay, now here's one of the things that's kind of cool about parametric equations with graphically. We can basically graph any function we want, anything that's already a function, by letting the first parameter be t and the second parameter be the function. So let me write this out so you can kind of see what I'm talking about, and then we'll go there. So basically what's happening is I'm letting x of t equal t, and then y of t equals, in this case, I'm going to do sine of t. Well, the reason this works is if we did eliminating the parameter, well, x is t, so basically I have y equals sine of x. So it's a quick little trick to be able to plot any function as a set of parametric equations. And that's what I have here for this first one. And we get our basic standard sine curve. I'm only going negative 10 to 10. That's plenty for what we're going to do here. We could, if we needed more, you just alter your t window. But what I want to show you that is kind of an interesting thing about being able to do it this way. This is not, sine over its domain is not an invertible function. It doesn't pass the horizontal line test. So when we do arc sine, we have to bound it in between negative pi over 2 and pi over 2. But because I've done my parametric equations this way, all I have to do to find the inverse is swap the x and the y. And then that blue graph is the graph of the inverse of the red graph. So defining a function as parametric equations makes finding the inverse very easy, because all you have to do is switch your x of t and your y of t. Very cool little trick that will pretty much always work. Okay. Let's see. Let's look at some interesting graphs. All right, so this is kind of cool. So this is 3 sine of 5t, 3 sine of 3t. Things that, again, we can't graph this in rectangular. So let's see what happens as we move b along. We get more and more of the graph until it starts repeating itself. So at this point, you're not seeing anything else drawn. It started repeating itself. All right, so again, this is definitely something we can't do with a function. We certainly can't have a function that overlaps itself. So these are the kind of things that we can do with parametric equations. I'm not going to spend too much time on this, but if you get a time to play around with these, you can make some pretty cool stuff, right? This is just a parametric equation. You want to see how it's drawn? There's one half, and there's the other half. All right. So pretty cool stuff that we can do with parametric equations. So, again, if you have time, it's something that's parametric equations are cool because you can create all sorts of stuff if you go look online, there's all sorts of stuff that's been created with piecewise sets of parametric equations, and you can find really interesting shapes, not just a heart. I think there's people who've done like the bat symbol and things like that. All right, let's get into some calculus with parametric equations, because that's going to be more of our focus. All right, so I'm going to take these parametric equations here. I'm going to let x of t equal 2 sine of t plus 1. This will look kind of familiar. It's similar to the example that was in the online lesson, but I wanted to go through one with you before I cut you loose on one. This shape is going to look really familiar from Tuesday, right? That's our ellipse as a set of parametric equations. Cosine sine, sine cosine. When they have the same number in front, like so, they make a circle. When you change those numbers, they make the ellipse. And guys, this is one that's really easy. If you sub these into those equations for the ellipse, because of the Pythagorean identity, it's really easy to verify that these create the ellipse that we're seeing. So ellipses are very easy to create in parametric. Circles are very easy to create. Hyperbolas, all the conics we looked at can be parametrized. Not going to be a major focus of what we're doing, right? It's not going to be a major focus of what we're doing here, but I just want you guys to realize that. So let's talk about our ellipse here. What we're going to do is let's find, if I can find the tangent line at x equals pi over 4. Excuse me, not x. I want to do t. At t equals pi over 4. Now, if we want to know where that is on our circle, let's just put it in as one of our limits. All right. So when we're at 0, we're starting at 0, 3, so up here. So our tangent line is going to come in right at about that point right there. Okay. And we know what a tangent line should look like, so we'll plot it at the end to make sure it works out. All right. Well, let's talk about what we need. We're going to be plotting this tangent line in the xy plane. So we need to find dy dx. Well, it's a nice little trick that we're going to do, and this will go not just for this, it'll also be for polar when we do polar next time too. Dy dx, well, we can do dy as dy dt and x as dx dt. Because if we think about dividing fractions, we flip the bottom and multiply, and the dt's cancel out, right? This would be dy dt. This is basically from our chain rule, dt dx. All right. So that's basically what's going on there. This all of a sudden makes things quite a bit easier to deal with. So that means we need, from our functions, well, we have x equals 2 sine t plus 1. So dx dt equals the derivative of this, which is -2 cosine of t. Y equals 3 cosine of t. So dy dt is 3 sine t. And we now have our derivative in terms of t. All right, so -2 cosine of t over 3 sine. I got those signs backwards, didn't I? Sorry, guys. It happens to me too. Derivative of sine is cosine. Derivative of cosine is negative sine. And let's fix, we can put the negative wherever we want down here just for consistency's sake. All right. So now we're doing this at t equals pi over 4. So we're going to plug pi over 4 in for t. So we got 2 times rad 2 over 2 over negative 3 over, oh my goodness. Guys, I'm sorry. Let me go back. You guys probably caught what I did. I got them upside down. Oh boy. Long week for me too. Sorry guys. All right, let's fix this first. So first off, let's get our derivatives correct. I have it written right here. I don't know how it's dy dt goes on top. Minus 3 sine of t over 2 cosine of t. This can be simplified, but you don't have to. We're doing this t equals pi over 3, pi over 4, excuse me. This is a different example. We're going to evaluate this at t equals pi over 4. So we get negative 3 times rad 2 over 2 over 2 times rad 2 over 2. How nice, those cancel. And there's our negative 3 halves. That is going to be the slope of our tangent line. Remember, tangent line needs 2 things, slope and a point that it goes through. Well, where are we going to find the point that it goes through? We're going to plug pi over 4 into our original parametric equations. So x of pi over 4 equals 2 times rad 2 over 2 plus 1. Those will cancel out, and we get rad 2 plus 1. And y of pi over 4 equals negative 3 times rad 2 over 2, which not much simplifying we can do there, minus 3 rad 2 over 2. So basically, our m is negative 3 halves, the point we need to go through. It's not pretty, but it's a point. And negative rad 2 plus 1, comma negative rad 3 times 2 over 2. And I'm just going to do this in point slope form. I'm not going to kill myself on it. So y plus 3 rad 2 over 2 equals negative 3 halves times x minus rad 2 plus 1. And now to plot it, I will have to move this term over to the other side. So I subtract that off of both sides. But I'm going to leave it in this form. This is a tangent line. And it's going to be something that we're going to cover later this semester. Things in this, tangent lines in this form, called Taylor polynomials. Very cool topic that is a lot of fun and has a lot of cool applications. There's our tangent line. Again, not pretty, but completely plottable. So let's see how we did. So this will be cool. We can kind of see the graph moving around as we put things in. So minus 3 halves times x minus square root of 2. Okay, we're not quite there yet. Slope looks good. Plus 1. Well, slope looks good, but we need to shift it. So minus root of 2. And we definitely have an error somewhere. Where did I make my mistake? Oh, right here, my y of t. That makes it easy. y of t was positive 3. I'm just thinking the negative. Jeez. Sorry, guys. Let's get rid of the negative. The negative. That'll make this negative. And guys, you know, I never want to make mistakes in here, but when you guys can learn from my mistakes, it's even better. How did I catch my mistake? By plotting it. I plotted it and said, whoa, something's off. And I can go back and I can fix it. All right, let's see what shifting this thing up does. And there we've got a nice, beautiful tangent line at roughly the point we were hoping we would have a tangent line at. Questions about that? About how to, take the derivative, find the tangent line. And Desmos is great for plotting parametric equations with rectangular equations. Okay. Then let's just do one more thing before I cut you loose, and that's just because, hey, we found the first derivative. Let's find the second derivative. The derivation is in the lesson, so I won't bore you with that. But a very quick way to find the second derivative in parametric is to do the derivative with respect to t of your first derivative over dx dt. What's nice about this, we've already got this, we've already got this, we just have to take the derivative of this guy. And check this out. Remember that our first derivative, let's kind of put it over here, note, dy dx was minus 3/2 sine t. Now you don't have to do this, but anytime we can simplify, we like it. Well, what's sine over cosine? Very nice, it's tangent. So minus 3/2 tangent of t. So to get our second derivative, basically we're doing the derivative with respect to t of tangent of t over dx dt, which we have right here. So over 2 cosine of t. Oh, and I forgot the negative 3/2. Wow. Let's get some, man. Absent-minded today, guys. I apologize. Negative 3/2. The derivative of tangent is secant squared. So we have minus 3/2 secant squared of t over 2 cosine of t. We can clean this up a little bit too, because this denominator, we can do it as secant or cosine, really, but secant squared of t. Now 2 over cosine, 2 cosine of t, this is the same as 2 over secant of t. So flipping by the reciprocal would be secant of t over 2. And we get, I lost my negative, didn't I? We get negative 3/4 secant cubed t. That is our second derivative. Again, it's in terms of t, but that's okay. If we needed to get t in terms of something else, that's when we go back and look into eliminating the parameter. But a lot of times that's what's going to happen with parametric equations. Your first and second derivatives will end up in terms of your parameter. So I just wanted to do that because it's not much more. Once you have the first derivative, you've done most of the work with the second derivative, so it's not that much more work. Okay, questions about this one? All right, so what we're going to do next, I'm going to have you guys work on a worksheet. So let me bring it over here. There's one thing I want to show you first. So down here, you're going to do a couple of tangent lines. So that's similar to what we just did. All right, but I want to talk about this first one, and maybe we'll do one of these together so you guys can get the hang of it. All right, so what you're being asked to do is, let's zoom in, and I put it in chat, so you can bring up a copy if you need to. For the parametric graph at the right, determine whether dx dt, dy dt, dy dx are positive, negative, or zero at these points. All right. Let's talk about how we do that. So what we're going to do is we'll make a little table. This is what I'd recommend doing. It's a good way to keep track of it. So you're going to have your t value. You're going to have 1, 2, 3, 4. And then in here, you're going to have your dx dt, dy dt, and your dy dx. All right, now how do we determine these? Well, dy dx is just like in the xy plane. So notice here at 1, our tangent line would have a negative slope. We already know, based off of what we've done in Calc 1, that's going to be negative. I'm going to show you another way of showing that it's negative in a second. But let's talk about how you do dx dt and dy dt. For here, what we do is we look at how y changes in the direction of increasing x. So right here, when we're looking for the sign of dx dt, so dx dt, it's asking about how is x changing in the direction of increasing t. Well, notice t goes 1, 2, 3, 4. So increasing t is along the path this way. It's not horizontal or vertical, it's along the path. So as we move in the direction of increasing t at this point, and I'll ask you guys this, is x, as we go in this direction, is x getting bigger, smaller, or staying the same? So we got one vote for each. And think about it, we're going in this direction, right? The direction of the arrow, so it's getting a little messy here, which is in the direction of increasing x. There we go. Very good, guys. X is getting bigger, which would mean that our derivative at that point would be positive. Questions about that? All right. Now let's talk about what happens with y as we move in the increasing t direction. Should the dy dt be positive, negative, or zero? You can put plus, minus, or zero in chat. So we're moving along t in this direction, right? The y's are getting smaller, so we'd expect it to be negative. Now remember, we can think of dy dt as being we can think of dy dx as being dy dt over dx dt. So we're doing a positive divided by a negative, a negative divided by a positive, which is negative. So the fact that we saw this was already negative checks out from our words here. All right. What I'm going to have you guys do in your groups, fill in the rest of this table, and then go on to number 2. I gave you there, you're going to have a little bit harder functions to find the derivatives of, but we've got some time to do this. I just want you to take your time, get your derivatives, create the tangent line. You can completely use Desmos to do this. And what you can do, let me show you how you might want to do this if you decide to use Desmos. So if we're going to use Desmos for this guy, which I highly recommend, it's a pretty cool program. Let's turn those off. What we can do is we can actually let R be a slider. So what we'll do is we'll let R t minus sine of t And see where it says add slider, we'll put R in as a slider. And comma, R, can't remember what the other equation is, times 1 minus cosine of t. And that's the beginning of our cycloid. And you can kind of see what happens as R gets bigger and smaller. Let's get some size here and do step one. Let's start this way and start at 0. Okay. All right. Did I those equations in the right? Let's see. I have one too many parentheses. Let's see what's going on here. I got something in wrong. Give me just a second. It's fixed. Oh, no, now I've got it messed up. All right. Oh, okay. So what R does is it increases and decreases the radius, right? But if I want to get my cycloid, I've got to increase T. So let's make it a little smaller so you guys can see it. And let's zoom out. There's our cycloid. And now as I increase this, and this is something, again, you guys can play around with. It's kind of cool. Oh, got a bad. All right, now here's what happens if we increase R. It increases the radius of the cycloid. And the parameter is how many cycles you're getting, okay? So you can actually put it in terms of R in Desmos, and you can actually put in your derivative in terms of R in Desmos if you'd like. But what you're going to find is if you want to check your answer, you could always set R to be a constant value, say something simple, something small like 2. And then you can plot your tangent line with it to make sure it checks out, okay? So you can check it the exact same way that I did. So you can catch if you have any mistakes like I had. Okay, questions about what you guys are doing in your groups? All right, let's get you trying this. And it's just these 2 problems. Obviously, if you have any questions, definitely, of course, call me in. If